Hello and welcome back to more chemistry learning for y'all people. Today we are going to talk about the modern model of the atom. It's also called the wave mechanical model. What we talked about last time was like the historical development of the structure and the shape of the atom, right? We went from like we went from the very beginning, didn't we? Man, we covered like the idea of atomos to the first atomic theory, J.J. Thomson, Rutherford Goldfoil experiment. Atoms are mostly nothingness. Like, what does that even mean? Like, what? It's crazy. Anyway, there it is. Atoms are mostly empty space. And then we had the Bohr model. Man, that's something else too, wasn't it? Well, as it turns out, every single one of those had a lot of truth and understanding in it. But as time went on and we learned a little bit more, we made better instruments. We were able to make better measurements. We learned a little bit more about the shape and whatnot of an atom. And so now we are left with what is called the wave mechanical model of the atom. But what we're going to learn now is probably not going to change. Like I said earlier, like we still don't know everything there is to know about atoms. Dude, we can go on learning about the universe pretty much forever. So, it's where we're at. The stuff we're going to learn about here in this class, however, I can pretty much guarantee is going to be on like full lockdown. This stuff has been, the stuff we're learning is like several hundred years old, and it's very, very well established. More than likely not going to go anywhere. So, without further ado, my goal for today is to go over the wave mechanical model, or like the modern atomic theory of the modern atomic theory of atomic structure, or modern theory of atomic structure. Dude, I'm just starting my coffee, so don't judge, okay? Anyway, here we go. Let's get started, shall we? All right, the first thing that we want to do is to define atoms based on this new theory, this like modern atomic theory, this wave mechanical model. And so we have to put a box around it so we can wrap our brain around it, because if we don't like define something, it's really hard to understand it. So we're defining atoms as there are three main points to atoms with the modern atomic theory. The one thing I want to hit here is that it is the smallest particle that can enter into a chemical reaction. This is pretty important, this part here, right? It's the smallest particle that can enter into a chemical reaction. Atoms are made of smaller things, but they can't enter into a chemical reaction, right? And those things that they are made of are protons, neutrons, and electrons, right? So those are the three things. Everything that you know of in this whole world is made of only three things: protons, neutrons, and electrons. Now here's the clutch thing. This word atoms, right? When that sound comes out of my face, I am saying, and I mean, that it is neutral, right? Atoms are absolutely neutral. What that means is that they have equal numbers of protons and electrons. They are the same number, and it kind of has to be, right? Otherwise, the entire universe would be nothing but static electricity, and we would be like stuck to the walls, which would be really difficult to do anything if we're always stuck to the walls and everything. So, if we use the word atoms, it means neutral. That means equal number of protons and electrons. And you notice I haven't said a thing about these guys, these little neutrons. You know why? Because neutrons have no charge. So neutrons can come and go, won't affect the charge not even one little bit. However, protons and electrons do have charge. Protons are positive and electrons are neutral. You got it? So you have to have equal number. If you have 4 protons, you have to have 4 electrons. Because if it's an atom, right? Because then all the positives cancel out all the negatives, and we've got ourselves a nice, happy, neutral atom. You dig what I'm saying? Isn't that great? So let's dig into electrons for a little bit here. So if you remember Bohr, right? He had this idea that electrons were spinning around in circles, right? Like planets, which really makes sense if you look at the rest of the world. They're spinning, but the reality is that they are not spinning. The reality is so much weirder. So what's really going on is electrons live in these cloud-like areas, and we call them orbitals. Do you notice how this is a different word from orbit, right? You got that? Watch. let's play around with words for a minute. Apple. Right? You hear that sound? Apple. That is apple. That sound keeps coming out of my face. I mean a nice, round, crunchy, unbelievably delicious thing. Cannot wait for harvest season in apples. You know what I'm talking about, right? It's a fruit, right? Watch this. Kitten. Kitten. Like kittens and puppies. Kittens and puppies. See the sounds coming out of my face now? Or not see, maybe not see. Do you hear the sounds coming out of my kitten? Puppy. You get it? That is not an apple. If you picked up a kitten and chomped into it, it would not be delicious, and I would report you right away. Don't do that. Right? So we use different words for different things. Right? Okay, so if you notice, the word orbital is not the same as the word orbit. These are two different words because an orbital is not an orbit. Okay? It is not an orbit. No. This thing where electrons go around like this, no. Like erase, look, that's the idea of electrons going around in a circle. That's you erasing them. Okay? That idea is gone. So here's the deal. An orbital is a cloudy-like area around the nucleus, okay? And it kind of works like the Tasmanian devil. Y'all know how like the Tasmanian devil, you get so excited, and he starts spinning around, until he's just like a cloud. He's like a tornado, right? You kind of think of it like that with electrons. They are moving unbelievably fast, and they're moving around the nucleus, but they're moving in like a wave function. What happens, it's easier and better to think of it electrons is not being a point or a particle moving around in space, but it becomes the cloud around the nucleus. That's the best way to think of it. That it no longer becomes a single particle, but is a cloud, a fuzzy ball around the nucleus that has a negative charge. That's the best way to think about it, okay? So electrons are there, but they're going around really, really fast. So fast that it does like think of it, the best like mental construct is like the Tasmanian devil cloud thing, okay? And it has a negative charge, right? Negative, like the opposite of positive, it has a negative charge. And it has what we call negligible mass. In other words, the mass is so small that we can ignore it, right? I think I talked about this before when we were talking about J.J. Thomson, like up there a little bit more. Where like the mass of an electron is so small compared to the mass of the whole atom that it's like worrying about the weight of a trucker's cigar smoke when he hits the weigh station. It's too small, man. Nobody cares. Negligible. Like we can just totally ignore it, right? So these things are small. They're wicked small. They do have mass, but the mass is so small that it doesn't really ever matter in any of our calculations because it's just so teeny weeny. Now, here we go. Look what I did here. See, I knew that was a good idea. That I did this. I made orbital into a vocab word for everybody. So now we have to know it. Like specifically. Again, because one of the things is when we have words and definitions, and why this class has so many definitions, it's like a huge vocab class, is because ideas are captured by words, right? We go back to like apples, kittens, and puppies, right? If I say the word apple, we all have this idea in our head of what an apple is. Same with kittens and puppies. We know exactly what it is. We know how kittens and puppies make us feel, right? So that's why we give them definitions, so that we know what it is and we can lock it in our brain and have a really good understanding of what it is. So here's the definition of orbital. It is the area around a nucleus where electrons are likely to be found. Do you notice that all we can say is that it's where electrons are likely to be found? It's not saying what electrons are doing. It's not saying exactly their behavior and their shit or anything like that. All we're saying is that it's like an area, like a cloudy area, where the electron is in there somewhere. Like we'll find it in there somewhere. Where? Nobody really knows exactly. Got it? So that's all we need to know about an orbital. Cloudy, fuzzy place where electrons live. And electrons are negative. Okay? So it turns out that this thing, the spinny thing, no, that's way too easy. Man, you dig into this, it's got like wave functions where the electrons are doing like all kinds of things that are like just, it does not match up with common sense at all, what it does. Like, so how can a single thing turn into a cloud? It's just what nature does. Nature is not here for us to make us feel good and feel smart. Nature is just nature, and we will be trying to figure it out for like forever, forever ever. So here's the deal. Moving on, atoms can gain or lose electrons, and then when that happens, they become ions. So do you see how this is a different word than atom? Once they gain or lose electrons, which can happen, right? So these electrons, they can like come and go. You can gain some, you can lose some. We'll talk a little bit exactly about why. But when that happens, it's no longer an atom. It is an ion, because atoms and ions are completely different. Like totally. It is absolutely a chemical change. The difference between a calcium atom and a calcium ion, a potassium atom and a potassium ion, and that's why we use different words. All right, we use apple for apple and watermelon for watermelon, because apples and watermelons are really different, right? That's why apples and giraffes have different names, because they're really, really different, like really, really different. So are atoms and ions. They are really, really, really different. And now here's the thing. Oh wait, okay, so this part right here, where it says that they have a negative charge. I want you to remember that electrons are negatively charged. Don't get angry at me. Don't hate the player, hate the game. Or you can hate Benjamin Franklin for making electrons negative, because here's what happens. Gaining electrons creates negatively charged ions, because electrons are negative, right? So as you gain more electrons, the number of the charge, like the number that represents the charge, becomes negative, which a lot of people associate as like losing. But really, you're gaining negatively charged things. And losing electrons will create positively charged things, right? Because if you lose a little bit that is negative, you end up like what's left over has lost some negativity and becomes more positive. Well, that's really inspirational, isn't it? Yes. And so when that happens, when electrons are gained or lost, we get new vocab word, we get ions. And an ion is simply an atom that has gained or lost one or more electrons, and then it turns into an ion, which is nothing at all like the atom that it started from, like not even close. You understand what I'm saying? Picking up what I'm putting down, riding away, feeling flow, digging the groove, smelling what I'm stepping in. Oh yeah. Okay, so here's how we figure this out. Like, how do we know what the charge of an ion is? And it's also really good to know what the charge of an ion is, because that's really going to determine how this thing behaves and what it does when you put it in a chemical reaction. How does it bond and blah blah blah, all that kind of good like chemistry stuff. So we need to know the charge of an atom, or ion, because, okay, charge of an atom, 0. Bam! Nailed it! All right, charge of an ion. It's really kind of simple. It's basically the charge from all the protons, which is all the pluses, and you put it together. That's what adding means. You put together with all the charge from the electrons, and you notice the protons are positive. That's all your positive. The electrons are negative. That's all your negative. You pop them together. Bam! Right? That's it. Oh, and the answer to this, the charge, it always goes. Wait, let's do a nice color. It always goes here. That's the charge. Right? That is how many electrons have. That's like the overall like addition of protons and electrons, and we can figure out if it's gained or lost electrons and how many. See, charge always goes in the upper right. Charge always goes in the upper right, and if there ain't nothing, that means it's 0, because 0 is like, ain't nothing, like literally. So here's how we do. So here is a sodium ion, right? It has a charge of plus, and if it's just plus, it's assumed that it's a +1. Chemists are lazy. So if it's positive, does that mean that a negative electron has been gobbled up, or has a negative electron been let go? We don't really care where right now. Yes, you're right. It means this one right here. It has lost an electron, and if it is +1, it has lost, because it's positive. And if it's +1, it has lost 1. You dig? See how that works? It's not that hard. And this one, oxygen ion with a -2 charge. So this charge is -2. It is negative. So remember, electrons are negative. So if the charge is negative, that means that. Oh, where did my pen go? That means that it's gaining. gained 2, right? Because it's plus, or it's because it's minus 2. And now this last one, this carbon here, there's 0 charge. So nothing means nothing. Nothing. Nothing gained or lost. You guys picking up what I'm putting down there? Excellent. Excellent. So far we've basically covered atoms. Equal numbers of protons and electrons. It's made of protons, neutrons, and electrons, but the fact that it's an atom means that the protons and electrons are equal, so there's 0 charge. However, these electrons can be gained or lost. And then we dug into what are electrons, right? Because if atoms are made of protons, neutrons, and electrons, let's start looking at electrons. And if they come or go, we got these ions. If electrons go, the ions are positive. If electrons are gobbled up, the ions are negative. I think that's what we've done so far, right? That's great. So also, electrons live around the outside, right? In this like cloudy ball around the outside of the nucleus, which is in the middle. Yeah, you dig what I'm saying? So let's dig into like what's in the middle. And you might ask, hey Stu, what's in the middle? Well, what's in the middle are nucleons. Nucleons are things that live in the nucleus. And thank God there are only 2, protons and neutrons. Maybe I'm hoping that that'll keep things simple. So let's just start digging into what we got here. The first one, protons. Protons are positive. They live in the nucleus, right? Because they are a nucleon. They live in the nucleus. It has a positive charge. And we have a whole new unit of mass because these things are so small. We use its own like weight system, and we call that separate weight system the atomic mass unit. The atomic mass unit. Like and it's just like any other weight system, right? If we're weighing out the mass of a human being, we would use kilograms. If we're weighing out the mass of like, I don't know, a blue whale, we're going to use tons. If we're weighing the mass of a grain of sugar, we use like milligrams. So we just need different units of measurement for like the different scales of things. We could measure this in kilograms, but that'd be like so different, so stinking small. And the last thing that we need to know about protons, other than the fact they live in the nucleus, they are positively charged, they have a mass of 1 atomic mass unit. The other thing we need to know that's really important about protons is that the number of protons identifies the element. It's literally like it's like the social security number for an atom. Do you understand what I'm saying? So no matter what happens on the outside, like if electrons are gained or lost, and it like becomes an ion, if what makes it that particular element is the number of protons. So do anything else you want to like the protons and the neutrons, whatever you want, it doesn't change the identity of the atom. Isn't that trippy? So like the thing that makes an element is actually the number of protons. I never would have thought it, but you know, there it is. Who am I to judge? Nature's weird, man. Wait, let's go with a weird color. Let's do that one. All right. So next are neutrons. Now neutrons are neutral neutrons. Positive protons. Neutrons. Again, because they are nucleons, they live in the nucleus, and because it's neutral, there's no charge. Neutron walks into a bar, orders a drink. Bartender says, for you, no charge. Get it? Come on! We're going to be here all year. This is hilarious. You should be laughing at that. Because it's a neutron. There's no... It's not because the bartender's nice. It's because... Anyway, moving on. This is a fun fact. A neutron is also approximately 1 atomic mass unit. So a proton and a neutron, man, they weigh exactly the same. Like exactly the same. So if you held up a proton and you held up a neutron on camera, they would weigh pretty much, for us, as far as we're concerned, they would weigh pretty much exactly the same. And the only main difference between them is that charge, the proton would have a plus and the neutron would not, which is weird. And so here's the thing also, is that protons identify the element, right? You can't, like, that's it. Like 6 protons, carbon. Nothing changes about that. However, neutrons, they can vary in number for the same element. So you can have more than one neutron. They vary in number. So you can have more than one set or number of neutrons in like the same element. So 2 atoms of carbon can have 2 different numbers of protons. That's a thing. And when you have the same element with different number of neutrons, we call that, or we call those, because you have to have 2 of them, we call those isotopes. Just like people who are like born and they are they're identical, we call them identical twins. You need 2 of them to have identical twins, right? You can't have one twin. They come in 2s. So isotopes also come in 2s. Isotopes are when 2 atoms have the same number of protons, but different number of neutrons. Because that can happen, because apparently neutrons really don't do anything for the nucleus other than, like, well, give it some stability. It's kind of one of the things we're trying to figure out in like modern day science is what exactly makes the nucleus stable. We know neutrons have a lot to do with it. Exactly what? Nah, we'll get back to you on that one. So here's the deal. So many words right now, right? So all this stuff that we talked about is going to be captured is going to be captured by words. And the first one is atomic number. This is the number of protons in a nucleus, okay? It's the number of protons in a nucleus. And man, this is what IDs an element. Okay, we got to know atomic number. It is the number of protons in an atom. And then atomic mass, well, this is different than atomic number because this is well, dare I say it, guys, this is the mass of an atom, right? And we just talked about the 3 things that make up an atom, right? It's protons, neutrons, and electrons. And let's start where we started with the electrons. How much mass do electrons have? I'll give you a minute to like scroll back up and look. I'll give you a second. No, seriously, scroll back up and look. I'll wait. Like hit like rewind or whatever. Okay, good. Great, glad you did. Yeah, almost none. Electrons have almost no mass whatsoever. So this atomic mass, right, can only be from the protons and neutrons, because those are the only 2 things in an atom that have mass of any significance. Do you guys understand what I'm saying? And the other thing that we have is atomic mass unit. Now, an atomic mass unit is how we weigh out the mass of an atom, because like I said, the mass of an atom is really, really small, so we have this new unit. Here's the story behind the unit. It is by definition, and unfortunately this needs to be memorized. You just simply have to memorize this. This is part of our Regents curriculum. You must memorize that 1 atomic mass unit is 1/12 the mass of carbon-12. Now you might be asking, Stu, what the heck is carbon-12? Well, I'm going to explain for you just for a minute. There's a little story here about history and chemistry and stuff. So carbon-12 looks like this. First there's C, that's for carbon. And down here we have 6, because that is the atomic number. This corner right here, always atomic number. We saw a little bit earlier up here in this corner. This corner up here, this is charge. This corner is always atomic number, and this number up here is always going to be atomic mass. So this is carbon. So because it's carbon, we know it has 6 protons, and the mass is 12. So it is the isotope carbon-12. Okay. Okay. Also, where'd I go? If this is the mass, which is equal to protons plus neutrons, and this down here is the atomic, that's the atomic number, which equals just protons. The way that we find neutrons is like this. Oops. There you go. Right? You dig what I'm saying? So that's what carbon-12 means. Carbon-12 means this whole shebang. It means it's carbon, 6 protons, a mass of 12, so therefore it has 6 neutrons, so that's nice. 6 protons, 6 neutrons. And way back in the day, as science was really sort of taking hold and becoming like standardized, right? We needed a way of measuring things that was uniform throughout everywhere. And this is like back in the day, way before cars. I can't remember exactly. I want to say 1700. I could be wrong on that. So who knows? It's a long time ago. But it was definitely back in the day when there was still like a fireplace in the lab, because that's how they kept themselves warm, right? They, like, everywhere had a fireplace. And this is like old like ink and quill pen kind of times. There was this dude named Avogadro. Now, Avogadro was a genius, like way before his time. He was so smart that everyone like thought that his ideas were so crazy and outlandish. Out he goes. And it turns out he was right. But what he did was he knew that carbon is easily accessible to everybody, because everybody had a fireplace, right? So you could just go in the fireplace and you grab some carbon, and any lab of like any skill at the time could easily isolate carbon-12. And so he decided, instead of saying like, okay, this thing is gonna like weigh 1 atomic mass unit, what he did was he defined it, and then like whatever that definition like was, however many number of protons and neutrons it took, he would figure that out later, because he knew he couldn't do that now. So what he decided to do, sorry, I'm backing up, I'm getting a little like I'm getting ahead of myself. So the story is, this guy Avogadro decided to use carbon-12 because any lab could get carbon-12 and isolate it. Does it make sense? So what he did then is he took 12 grams of carbon and he put it on a scale. Does that make sense? Because then he knew that like it was like however many grams were on there, right? He could like divide it by 12, because that's how many nucleons there were, and he'd be like, however much one of those nucleons weigh, then that's how much the atomic mass unit is going to be. And that's basically the story of it. And then we're going to come back to the story a little bit later when we talk more about Avogadro. But he basically took carbon-12, divided by 12. That's your atomic mass unit. Why carbon-12? Because it was easily accessible to people of his time. Like a lot of these things, like definitions and whatnot in science, are like completely dependent upon what people can get at the time, whatever they can get their little dirty hands on. You guys get what I'm saying? Awesome. Let's move on to this thing. So we spoke about this a little bit before about isotopes, right? So I want to spend a few minutes talking about isotopes, because we've got atoms, we've got ions, we've got electrons, protons, neutrons, things that go all over the place, and that gives us atomic number, atomic mass unit. It also gives us charge, all kinds of good stuff happening here, man. So now we're going to dig into isotopes, because that seems like something we should look at, right? When electrons come and go, we get ions. So we dug into ions. Well, if neutrons can come and go, let's dig into isotopes then, right? Because that might be something weird. So what exactly is an isotope? Like I said before, an isotope is an atom with the same number of protons. This means same element. If it has the same number of protons, it's the same element, because you remember the number of protons identifies the element, but it has a different number of neutrons, and because of that, it will have a different mass. Right? Because if protons and neutrons both weigh 1, if two isotopes have a different number of neutrons, one will weigh different than the other, because they have different amounts of stuff that make them. You understand what I'm saying? And what's crazy is that many isotopes can exist for the exact same element. So like, for example, this lithium has 3 protons, right? Because there's our atomic number. The atomic number always goes here. 3, 3, 3. That's what makes it lithium, right? And the fact that they're isotopes, the thing that makes these isotopes is that if you look up here, the mass, 6, 7, 8, there are 3 different masses. Therefore, there has to be 3 different numbers of neutrons. So let's figure out how many neutrons are here. If you have 6 protons and neutrons and 3 neutrons, you will have 3 neutrons. See how nice that works out? That's one of the reasons why we use notation like this, because it's very simple to figure out how many neutrons you have, right? 4 neutrons in that bad boy, because it's just 7 minus 3. In this guy, it's 8 minus 3. There are 5 neutrons, right? Let me count. 1, 2, 3, 4, 5 neutrons, right? Absolutely. This one should only have 4. 1, 2, 3, 4. Look, I'm right. This one should only have 3. 1, 2, 3. Oh my gosh. It's like I've done this before. Right, so these are 3 elements, or 3 isotopes of the same element. They are not 3 elements of the same isotope. These are 3 isotopes of the same element, which means they are all the same element. They have the same number of protons, but they have a different mass because they have different number of protons. You guys get what I'm saying? And so here's the deal. You're going to look at the periodic, if this happens all the time where people look at the periodic table, and this number up here on the periodic table is like a decimal, right? Which is, what that means is it's an average, right? The periodic table gives us the average mass of all the naturally occurring isotopes of that element, and it is a weighted average. And we're going to look at that next time, how we calculate that out. But for right now, let's look at these 3 guys. Here, what I want us to do is I want us to name these, right? Now, these are obviously 3 of the same element. These are obviously 3 carbons. How, you might be saying, Stu, how do we know that these are 3 carbons? Two ways. One, we have the big capital C, that's the symbol for carbon, and also each has 6 protons. Does that make sense? So if it has 6 protons, it's called carbon. Like, that's it. It's carbon. This is carbon, this is carbon, and this is carbon. But they are not exactly the same, so we can't call all 3 of them carbon, right? You can't do that because they are different. And because they're different, you have to give them different names, okay? So this guy, so what is the only difference between these 3 carbons? The only difference. They're exactly the same chemically. If you look at them, they look exactly the same. If you chew on them, they taste exactly the same. If you take this carbon and bash it up into charcoal, they burn exactly the same. But if you put them on the scale, they will each weigh differently. So that's what we use. We use the mass to differentiate between the 3 isotopes, right? So this one has a mass of 12, so we call it carbon-12. And that's how we identify that particular isotope. Now, the one in the middle, this has a mass of 13. So we call that carbon-13. And the last one way over there, with a mass of 14, we call that carbon-14. Yeah? So one quick little thing. If you look at the periodic table, carbon is like 12.01 or something like that, like atomic mass units. So what does that tell us? What does that tell? Which one do you think there's most of? Is carbon mostly carbon-12? Is carbon mostly carbon-13? Or is carbon mostly carbon-14? If it's 12 point, that's supposed to be a 0. That's so bad that makes me upset. It's 12.01. I'll give you a minute to think about it. Yes, it's mostly carbon-12. Very nice. We're going to dig into that. Oh, not now, but maybe next time. Yeah, you made it to the end. Ah. So, the 2 things that we are going to work on next time. The first, isotope notation. And that is practice counting protons and neutrons and doing the proper kind of notation. And the next one, ions and isotopes, which is pure counting. Because you got to be able to like crank it out like that. I want to know how many electrons gained or lost based on the charge. If I give you the element, you should be able to tell me the protons and the number of neutrons and all that kind of good stuff. Well, actually, if I give you the element, it's just protons. If I give you the mass and the element, then you should be able to do protons and neutrons. And we will look at these and dig into it and help you out how to figure all that out in class, okay? So these are the two worksheets that we're going to be working on. That was the wave mechanical model, and I hope you guys have an awesome day. Arrivederci.